we now know that the goal of the problem is for us to actually be able to find the force box 1 is pushing on box 2. Right? That means the best system for us to choose in order to see this force is box 2. So we could see how box 1 is actually pushing on that system. All right? So I'm going to pick box 2 as the system. And now if we look at the problem solving strategy, we could see how we've identified the goals. We have a picture that already helps us visualize the situation. And now we just need to be able to simplify the situation with diagrams before we apply our mathematical model. So I'm going to pick box 2 as the system. All right, and I'm going to draw a force diagram for the system so we could see how all the different things in the picture are interacting with box 2. And I'm going to start off by always drawing the one thing that's affecting all objects invisibly. That would be the Earth that's exerting this gravitational force on this system. And then I'm going to be careful about my magnitudes and bear in mind that the floor below box 2 must be pushing on it too. And I know the floor exerting this normal force is pushing as hard as Earth is pulling down, since box 2 is not accelerating vertically. Now, here's an interesting question. We don't actually know if this person is causing box 2 to accelerate or not right now. So I'm going to just draw my force diagram, assuming there might be an acceleration horizontally. So that means if I assume that the situation is that the boxes are accelerating to the right, then that means my forced box 1 that's pushing on box 2 to the right, which is our goal, would have to be larger than the frictional force. It could also be the case where maybe the frictional force is larger and these two boxes are slowing down as the person is losing energy to keep these boxes moving forward, or it could be that the frictional force is equal in magnitude to the force 1 exerts on 2 if the boxes are moving with a constant velocity. So we won't know that until we find acceleration. But it does point out how right now one important thing we need to figure out is how much acceleration there is in order to finish off this situation. So now that I have a diagram, let's set up the situation and see if we could solve for anything. So Newton's second law is that acceleration is equal to the sum of the forces. If you add up all the forces and divide by the mass, that is what Newton's second law says, because forces and mass both affect how much acceleration the object has. And what we care about is a horizontal force. So that means I'm going to apply Newton's second law only along the horizontal direction. So we don't know the acceleration yet. So I'm going to leave that as a variable. We're going to add up the horizontal forces, and over here we could see how there's only two horizontal forces that I need to add into my situation. The goal, which is force 1 on 2, and the frictional force, which I'm going to say is negative mu times normal. All right? And this divided by the mass will be equal to the horizontal acceleration. So it seems that we have some of these, we have some variables. For example, we have mu, right? We have the normal force, because we know the normal force is equal to mg here, since the normal force the floor exerts on the box upwards is equal to the force Earth exerts on the box downwards. We also have mass, but here's the issue. We seem to still need two variables in this situation. We need to find the acceleration, and we need to find our goal, which is force 1 on 2. So when you set up a math equation and you realize that you have two unknowns, it means you need to be able to set up another math equation in order to solve for your system of equations. So how would we find acceleration? Well, if we look at the motion, I imagine that box 2, if it's moving, it's going to have the exact same motion as box 1. So let's pick a system that would be very easy to analyze. And I think the system that might be easiest to analyze in this situation in order to get rid of as many interactions as possible would be to pick a system of both boxes at the same time. We're allowed to pick whatever system we want, and you want to be able to pick the simplest thing to analyze. Over here, if we pick both boxes in our system, then we don't have to worry about how the boxes are pushing on each other yet. So that might help us find acceleration right now. So I'm going to set up the equation for both boxes right now. And right, so the system is going to be box 1 and box 2 at the same time. The outside objects affecting these boxes would be, once again, Earth, the floor, and the person. So if I draw a diagram for this, we could say that Earth is going to exert a very large force on both these boxes, right? The ground exerting what we call a normal force is going to be upwards. And then we could now also just look that the person is going to be pushing to the right. That's easy. And there's going to be a frictional force to the left. And once again, because we said we'll assume acceleration for right now, we'll say that these forces are different in magnitude. All right, so this is all the forces affecting both boxes at the same time. We could set up Newton's second law again, and hopefully if we find that acceleration, that horizontal acceleration in this case, we'll be able to actually solve for the acceleration. So we do have the force person exerts on the system, and we do have we could find the frictional force because we have mu, and once again we could actually find this normal force since it's equal to mg if we look at the force diagrams and check the magnitude of the vectors. So doing that, I'm going to set up my equation. The mass of the system is going to be the mass of both boxes, and we're going to add that, and the sum of the forces goes on top, so force person plus the frictional force of the floor. All right, so if we break this down, force person, I believe, was how much? The force the person exerts on the box was 150 newtons, and it's going to be in the positive direction. The frictional force is going to be in the negative direction, and it's going to be mu times normal force, where mu is going to be, I believe, if we take a look up here, 0.2. And the normal force, well, we know the force of Earth is going to equal to be m times g, and the mass of our system is both boxes together. So we got the 40 kilogram box plus the 20 kilogram box. I believe I got that correct. Yep, 40 kilogram, 20 kilogram. So 40 kilogram, 20 kilogram box times 10. So that's going to be 60 times 10, or 600 newtons of force. All right. And then finally, now we divide that by the mass. The mass of both boxes together would be 60 because, once again, we chose the system to be both boxes. And now setting up, we could see we did just find the acceleration. The acceleration here is going to be 150 minus 0.2 times 60. All right, so 0.2 times 60, that would be 120, and then over 60, and if we solve, we got 30 over 60, and we got the acceleration is equal to 0.5 meters per second squared, and we say the acceleration's in the positive direction. Does that make sense? We needed this acceleration before, and we could see that, yes, we did assume the acceleration would be in the positive direction, and we can now see that the acceleration is there. So, going back to the original problem, now that we have the acceleration, we could solve for our goal. So our acceleration is a positive 0.5, right? And for the rest of the problem, it's just going to be a little bit of algebra, just like what we did before. The coefficient of friction, once again, was 0.2. The normal force was over here. Well, over here, once again, we want to find the normal force, which is equal to mg, except our system, in this case, is going to be only box 2. So what is the mass of box 2 for our system that I've been drawing in red? The mass of box 2 is 20 kilograms. So 20 kilograms times g, which is 10 meters per second squared. That's going to be 200. divided by the mass of just the system. In this case, the diagram in red was just box 2. So that would be 20 kilograms. And bear in mind, as long as we are careful about what system we're analyzing, all our math should be working well together. I'm just going to check my math one final time, and I do notice a mistake. The one mistake is that the frictional force has to be negative. So over here, I forgot to include that direction, so I'm going to include it right now. And what we have now is we're going to solve for force 1 on 2. Multiply both sides by mass. That would be 10. Add friction across. That would be 40. I believe 40. And could that set that equal to force 1 on 2. I didn't show my algebra, but I believe you guys are capable of that. So we could actually see how the final answer is 50 newtons. 50 newtons is equal to force 1 on 2. Alright, so we applied our mathematics, and now let's check if our answer makes any sense. So if this is 50 newtons and we have an acceleration that, once again, you said is going to be pointing to the right, then let's check. It should be bigger than the frictional force. How big did we say the frictional force was? Well, the frictional force, according to our mathematical setup, was equal to 40 newtons. And we could once again see that it seems to make sense, where we are getting an acceleration since our net force is towards the right, causing an acceleration that's also going to be towards the right. And we could actually see how all of this seems to fit together. So, number 2 is identifying the third law pair. So technically, there's one more way we could check our answer. We could check our answer if we wanted to analyze box 1. All right. So if we analyze box 1, we should notice that box 1 has the same acceleration as box 2, and likewise, force 1 on 2 should be equal to the same amount of force that 2 is exerting on 1. So if we go back to box 1, I'm going to actually analyze box 1 next. And at this point, if you wanted to see how we analyze box 1 by setting up Newton's second law all over again, you could keep watching this video. Otherwise, we have already finished the goal for the problem. So to practice Newton's third law, system now of just box 1. If we analyze the forces, this one's a little bit more tricky. We got the gravitational force, we got the normal force, all right? So Earth on box 1, floor on box 1, we got the person pushing to the right, and we know that the net force has to be to the right, so let's see if that makes sense. The frictional force is opposing it, but we also said that up here, force 1 on 2, well, force 2 on 1, if it's a third law pair, should be the same magnitude. So this is our frictional force the floor exerts on our box 1, and then 2 on 1 should be the same in magnitude. So force 2 pushing on 1, and we can see how it's also in the opposite direction. Right? This force is the opposite direction of this force, but identical in magnitude. And we now know that this should be 50 newtons, except in the negative direction. And the force the person exerts forward should be a larger amount, which is equal to 500 newtons. And let's just check, is the acceleration adding up? So here we go. I'm going to set up Newton's second law. Acceleration horizontally is equal to sum of the forces divided by mass. That would equal force person plus negative force of box 2 pushing on box 1 plus the frictional force, which should also be negative. So this would be 0.2. It's negative. This frictional force is negative because it's pointing left. So negative 0.2 times the normal force. What is the normal force? You can see once again it's going to equal mass of box 1 times g, because the downwards force of Earth down here is equal to the upwards force of the normal force in this case. So let's finish off this calculation. Box, that's 40 kilograms times 10 meters per second squared, so that's 400. And divide by the mass of our system. Our mass is box 1, so we would only be dividing by the mass of box 1. And we expect the acceleration to be the same as the other boxes, so let's do all our calculations. Force of the person was, not 500 newtons. Force of the person was 150 newtons, I believe. You could check with the problem above. So we got 150 plus negative 50 plus 0.2 divided by 40, that's what, I think 80? Except in the negative direction, all divided by 40. Does that give us the correct acceleration? So let's check. We got 20 over 40. And now you could actually see the acceleration is did match up with what we expected. So we could see how you could apply Newton's second law for any system of your choice, and if you apply it correctly with a correct force diagram, and if you apply it correctly with the correct directions in your mathematics, that all of your answers should be consistent with each other. So I hope this helps you guys understand how to see third law pairs between objects. Once again, third law pairs is not the normal force and the gravitational force. They will always be on different objects in the system. So in this case, box 1 pushing on box 2 and box 2 pushing on box 1, and you'll see them on different force diagrams. Right? So I hope this helps you guys figure out how to set up Newton's second law for any chosen system, and how to set up a system of equations if you notice you have multiple variables that are not solved for.